This is a video about Kepler's first law, specifically how objects move through space, the shape of their orbits, and some common misconceptions about orbital motion. My name is Mr. Head, and welcome to MN Horizons. Solar system diagrams are often simplified to streamline the learning process, but these oversimplifications can create misconceptions that are important for us to understand. The first misconception revolves around scale. In simplified diagrams, the planets are shown much too large when compared to the Sun. The distance between planets are also compressed to help learners better visualize planetary motion. If I were to adjust this diagram to be drawn accurately to scale on a screen, the Sun would end up only a few dozen pixels across, and the Earth wouldn't even take up a full pixel. Because of this, we'll switch back to a not-to-scale diagram for the purpose of this lesson. The second oversimplification involves the motion of planets. We often show planetary orbits as perfect circles, again for the sake of simplicity. But mathematically speaking, perfect shapes are rare in the real world. There are many factors that affect Earth's orbit, including the gravitational influence of other planets such as Jupiter and Saturn. When these planets are closer to Earth, their gravitational pull has a slightly larger effect, subtly modifying Earth's already elliptical path around the Sun. Because of this, planets actually orbit in geometric shapes called ellipses. Put simply, an ellipse is like a circle that has been slightly flattened. An ellipse should not be confused with an oval, which has no precise mathematical definition. Mathematicians define an ellipse very precisely. An ellipse has 2 points called foci. For an ellipse, the sum of the distance from any point on the curve to the 2 foci is always constant. In the diagram, you can see lines drawn from the 2 foci to the edge of the ellipse. As the individual distances change, their total remains the same. One unique feature of planetary orbits is that the Sun is always located at one of the foci. This leads to some interesting effects that we will explore further when we discuss Kepler's second law. There's one last misconception to address, and that relates to eccentricity. Eccentricity describes how stretched or squished an ellipse is. The diagram we used earlier shows a highly eccentric orbit to clearly highlight the difference between a perfect circle and an ellipse. In reality, however, planetary orbits have much smaller eccentricities. A perfect circle has an eccentricity of 0. In our solar system, Mercury has the largest eccentricity at about 0.206, still much closer to a circle than most ellipses we draw, while Venus has one of the smallest at about 0.007. When shown on a screen, both orbits appear nearly circular, but at an astronomical scales, even the smallest differences can matter. Even with Venus's very small eccentricity, the difference between the length of its major and minor axis is on the order of 5,000 kilometers. That difference is large enough to be significant in precise scientific measurements and studies. To summarize, planets do not move in perfect circular orbits. Instead, they follow elliptical paths with the Sun located at one of the foci. This idea is a critical foundation for understanding Minnesota Standard 9E2211. Use mathematical and computational representations to predict the motion of natural and human-made objects that are in orbit in the solar system. Thanks for joining me on MN Horizons.